What's going on, smart people? You've probably heard someone say before that all squares are rectangles, but not all rectangles are squares. A slightly less common phrase that you might have heard is two index tensors can be projected onto a coordinate system and represented by a square matrix, but not all square matrices are tensors, or not all matrices are tensors for short. I don't know why that one hasn't caught on as much. And this is a pretty confusing concept considering a lot of times tensors are introduced to physics students as matrices. So today we're going to take a look at an example. We're going to take a look at a square matrix and we're going to see if it transforms as a tensor. Alright, so this is a 2x2 matrix constructed from the Cartesian components of the two-dimensional position vector. So here, x1 is x, x2 is y. Is this matrix a tensor? Now before we get started, the first thing to consider is you have to agree upon a group of transformations that the object has to transform as a tensor under, which a lot of people forget to mention. So things like the inertia tensor transforms as a tensor under orthogonal transformations. So objects that are represented in an orthonormal basis who transform as tensors under orthogonal transformations are called Cartesian tensors. Now, since we are representing this matrix in an orthonormal basis in Cartesian coordinates, flat space, we're going to be checking if it is a Cartesian tensor. There are more general tensors than a Cartesian tensor, but if this fails to be a Cartesian tensor, then it definitely fails to be a more general one. So let's go ahead and label these matrix elements. So we're going to say we're collecting all of the matrix elements into a matrix, which is what this bracket is saying, of the matrix elements that we'll call L and M. Sorry, it's a little squished, but that's the LM matrix element collected in a matrix. Is it a tensor? Well, let's go ahead and write down how tensor components should transform. So in the primed frame, we'll call it T prime ij. This is equal to the transformation coefficients for a two-index tensor, which are the partial derivative. We have doubly contravariant indices, so it's dx prime I dxl dx prime j dxm times the unprimed, the regular, the old representation in the old basis, tlm. So we have repeated indices in the denominator and the numerator, so this is what we're summing over, which means all that's left over is the primed I and j, which is what we have here. Cool, so this is how a two-index tensor should transform, and we're saying we're limiting ourselves to orthogonal transformations, so let's see how it transforms under rotations. And we know how Cartesian components of vectors transform under rotations. We just got x prime 1 is equal to x1 cosine theta plus x2 sine theta. Okay, and x1 is just x, x2 is y, or x1 is x, x2 is y. Okay, and x prime 2 is equal to minus x1 sine theta plus x2 cosine theta. You may have seen the signs swapped for these two terms here. One just corresponds to a rotation clockwise, one corresponds to counterclockwise, so it doesn't actually matter. So this is our rotation. Now we just need to calculate the transformation coefficients. We have to calculate these dx prime I dxl's. Okay, so we'll write that down here as trans coef. Okay. So we're taking derivatives of the prime coordinate with respect to the unprimed coordinate. So for example, dx prime 1, dx1. Let's calculate what all of these are. dx prime 1 dx1 is equal to cosine theta. I'm just taking the derivative of this with respect to x1. dx prime 1 dx2 is equal to sine theta. And the same thing goes for these. So dx prime 2 dx1 is equal to minus sine theta, and dx prime 2 dx2 is equal to cosine theta. Great. And we actually have all of the pieces already to find out if these components transforms as tensors. So let's go ahead and do this. Like I said, we're summing over L and M, so we're going to have four terms to calculate here. So say if we want to calculate the 1, 1 component in the primed frame. Let's see if the 1, 1 component in the unprimed frame transforms as a tensor. So if it does, T prime 1, 1 should be equal to x2 prime squared, because we're just going from the unprimed to the primed. So this is what we should get if it transforms as a tensor. Let's see if that's what happens. So this is equal to, we're just going to sum over L and M. It doesn't really matter which order. So let's do dx prime 1, dx1, dx prime 1, dx1, t1, 1, plus dx prime 1, dx1, dx prime 1, dx2, t1, 2, plus, see, a lot of you, I think in this notation it's kind of abstract to really see what you're doing, but here we've already calculated all of these and we know what these are. We're just multiplying together and see if left hand side equals right hand side. So plus dx prime 1, dx, so that's 1, 2, so let's do 2, 1, prime 1, dx 1, t2, 1, and I'm really not going to be able, I can fit this, you guys know what this is, plus dx prime 1, dx2, dx prime 1, dx2, t2, 2. Okay? Now we can just plug in all of our transformation coefficients and the corresponding matrix elements here and see what we get. So this is equal to cosine theta, so we've got dx prime 1, dx1 is this, and then again, so this is just cosine squared theta, times t1, 1, that's just this matrix element here. So we've got x2 squared, yep, on to the next one. Sorry, I got scared because I actually recorded this video one time already, and the recording just stopped 10 seconds in. It's really frustrating. Okay, now these next ones. So this is plus cosine theta, sine theta, just got dx prime 1, dx2, t1, 2 is right here, x1, x2. This we're actually going to end up getting the exact same thing. dx1, dx2 is cosine theta, or sine theta, sorry. That's just this term. dx1, dx1 is just cosine theta. So just to be more suggestive, I'm going to write it as cosine sine again. Cosine theta, sine theta. t2, 1, so row 2, column 1, x1, 2 again. x1, x2. And the last term here, so dx2, dx2, so that's just sine squared theta times the matrix element. t2, 2, x1 squared. Okay, but we can simplify this a little bit more because we've got two repeated terms here. So this is just equal to cosine squared theta x2 squared plus 2 cosine theta sine theta x1, x2 plus sine squared theta x1 squared. Okay. Well, so for these components, if this component really does transform as a tensor, there should be a way of showing that this is equal to x prime 2 squared. And we know what this is. We already have x prime 2 right here. This is just the transformation from unprimed to prime. So if we square this, we should just see if the square of this equation is equal to what we have here. So let's go ahead and do that. So the square of the first term is going to give us an x1 squared. So x prime 2 squared is equal to x1 squared sine squared theta, because the negatives cancel, and that looks good so far. It's x1 squared sine squared theta, so that looks good. And then we've got a plus x2 squared cosine squared theta. And that looks good again, that matches that perfectly, looking good. And then we've got minus, because we've got a minus and a plus here, so we've got minus 2 x1, x2 cosine theta, sine theta. And there it falls apart. Just like that, we've got a minus sign here, we've got a plus sign here. The left-hand side does not equal the right-hand side. This is not a tensor. So, to recap, an object is a tensor if its components transform as tensors. What we did is we took the first element of this matrix and did an orthogonal transformation, more specifically a rotation on it, and expanded it. That's exactly what this term is here. And then we took the primed frame and expanded that, which is what this represents. This is just the primed transformed coordinate. And we showed that the left-hand side does not equal the right-hand side, therefore this matrices components do not transform as tensors. Now, something that I think that you could chew on for a little bit. This is our rotation. But say that we didn't use these transformation coefficients. What if we were a bit more general? What if instead we just assumed that x prime 1 is equal to x1 a1 plus x2 a2 x prime 2 is equal to x1 a3 plus x2 a4. Is there a type of transformation, this is a pretty general one, is there a type of transformation that this matrix does transform as a tensor under? The person that answers this correctly, I will pin the comment so that others can see. I'm sorry, I'm too poor to do anything else. So let me know in the comments section, if you take some arbitrary constants instead of these sines and cosines and treat the transformation this way, is this enough? Are there conditions that you can place where this matrix will transform as a tensor? Let me know in the comments section, and I'll see you guys there.